Yes.
Okay. All right. So as I mentioned, the name of our group is Visual Computing Lab, and we work on several application areas of machine learning, and we look into visual analytics problems very similar to what Professor Venkatesh Babu and his group members at Val Lab do, and I will not, we also have very strong collaboration across these two labs, and I will not talk about, the problems that we work on together. Some of them we will touch upon. And, whatever we do in our lab, I mean, all these applications can broadly be categorized into, one of the three main areas that, we can think about. And we like to call them video surveillance, wide area video surveillance. And the second area is basically what we call data efficient deep learning. And we will see there are several problems that we have worked on. And finally, one area that we are very interested about lately, which is marrying, computer vision or visual data as a modality with other modalities like let's say text, natural language queries, etc., and solve problems at the overlap of these multiple different domains. And we also work on domain adaptation, so basically cross-domain learning problems. So we classify that third group of work as a cross-modal / cross-domain learning problems. Right. So most of you already know what video surveillance is because you encountered that every day. For example, in shopping malls, in airports, everywhere, and that is one of the key areas of application areas of modern video analytics or computer vision. So you have seen all these CCTV cameras, and they are capturing video feeds 24/7. And the traditional way of analyzing these video feeds to understand what's going on, to monitor a situation, as well as potentially to avoid an untoward situation, also do forensics on these videos, or potentially solve a crime basically based on these video feeds, because you are supposed to store these video feeds for quite some time. Right. So all these things can happen manually, right? But these, huge amount of video data is there, which is not possible or very cumbersome for many human operators to analyze and study, right? And it's not a humanly possible, effort. For example, take this problem as an example, which is called person re-identification, right? Which is a very common, wide area video surveillance problem. Suppose, there are many cameras, and this first set of, set of frames here on the left is basically one video feed that is being captured in some campus like IISc, right? And what you want to do is that you want to not only detect this, all these human targets in these video feeds, but you also potentially want to recognize them in a later time or at a later place, right? Or a different place, which might be, a different camera field of view. So that is exactly what a re-identification problem is. That is, once you detect these human objects using, let's say, a modern object detector, right? And that constitutes a whole lot of, detected object images, or human images in this case, which we call a gallery set. Now, you want a person of interest to be monitored across these different cameras in this, campus. So once you recognize who this person is, and then you want to, search for this person across many different cameras, this basically, is a re-identification problem, and the goal is to get in an automated manner a ranked list of candidate matches, whereas the top ranks are basically supposed to be the correct, retrievals, right? So it's basically a retrieval problem. Now think about the scale of this problem, because there could be thousands of, visitors in a shopping mall. And even when you want to find out somebody in 4-5 hour time window, it's very difficult, especially if there are more cameras, like 10, 15, 20 or 100 cameras in that shopping mall, right? So it's a cumbersome problem to solve manually. And so what happens is that this modern there are many modern re-identification frameworks, deep learning based re-identification solutions that are already existing, which give even in some cases better than human performances, right? Understandably so. Now, one issue with such a system is that if there are 10 or 100 cameras in a network, they basically query each of these cameras independently, right? So they combine everything together and then they query the entire gallery set. Now, one concern in that is that when you query like that, and all you have is one image of a person, let's say, right? And when you do some sort of one-time querying across all these cameras, the problem is different cameras may capture the person in various different poses, various different scales, resolutions, etc., illuminations, and the challenges will be different across different cameras. And one image may not even match. For example, this person is carrying a backpack is hardly seen in this image, in the query image, whereas in this camera too, it is the right, the purple box is basically the right retrieval, right? And in that case, the person is carrying a backpack and looks very different if you just look at the image content or the appearance, right? Now, how to get benefited? So the point is, when we query a camera, you get the retrieval results, and let's say there is a human operator who says, okay, fine, this is basically the right retrieval, and clicks on that. And then what happens is that this query image takes into account this other retrievals from other cameras and learns, a better holistic representations as you are combining, observations with complementary information, right? Complementary semantic and visual information, and thereby you get a more robust feature to query the other cameras. So basically, you do this thing sequentially, and you can show that you can end up getting better and better retrieval results as you combine more and more queries, right, from different cameras. So another area where we wanted to explore in recently is one of the open problems in person identification community, where you want to not only do daytime surveillance, right? You also want to do nighttime or low light surveillance where there is hardly any light available, right? So basically, what happens is that most of the modern re-identification data sets, they are captured using standard PTZ or CCTV, static CCTV cameras, which are basically RGB cameras, right? So they capture images in the visible spectrum, right? However, if there is almost no light in a scenario, consider a situation where you want to monitor the entrance of an apartment and at night, and there is hardly any light, right, there at night, and a person who comes in and goes out, you will hardly be able to get any visual, information, especially if you consider visible spectrum, right? So in such a situation, people have sorted to this thermal cameras, basically, which captures, these kind of images in the bottom row, and all you want to do is to match, these or do re-identification across this visible as well as this infrared or thermal spectrum, right? And which is a non-trivial problem, because a standard model which is trained on visible spectrum images, regular cameras, they will not work well because they look very different if you look at the corresponding thermal camera images of the same person. So that's where we propose something called MMD ReID, which is basically motivated by the maximum mean discrepancy. It's a widely used statistical tool for hypothesis testing that aims to determine the distance between two distributions, right? And basically, it uses some sort of a novel, margin-based formulation to match the feature distributions of visible as well as thermal samples and minimize the intra-class distances while maintaining feature discriminability. It's a very simple framework, but we see that, even with this kind of a simple framework, you can potentially get a fantastic improvement in the visible to thermal person identification performance, right? The other re-identification problem that we wanted to look at is where you do not have a lot of label information. So how do you train such a model, right? Think about it. So re-identification is an open set problem, right? So the let's say you have a training data, you have 1,000 different person identities across 6-7 camera field of views, right? Now each of them, these persons have an identity and so on. Now at the test time, you cannot expect to have the same identity person to come in, right? Because think about that shopping mall experience. Every day, every hour, a new person is coming, right? Or an airport for that matter. So there will be a disjointedness or even a complete non-overlap between your test identities as well as your validation or train identities and validation and test identities, right? So, but even then, you need to be able to annotate these samples across these different cameras. That okay, this is the image of person 20 in camera 1, and this is the same person 20 in camera 2, and you have to actually go through all these camera feeds, and again this whole annotation is going to be a difficult task, and that deep networks require a lot of annotation to work very well. So this gives rise to this whole domain of unsupervised person identification, which tries to basically cluster these targets, learns to cluster these targets into these different buckets, where each bucket will contain the identities, the images of the same identity target. Right, and basically, we proposed really recently an unsupervised person identification solution with zero knowledge on the true levels, right? And it follows a two-stage training strategy. And the first stage, as you can see, involves training a deep network on some sort of a post-transform data set. So, for example, you can think about each image because you don't have any level information. So you can start by assuming each image to be its own class, right? Although that's not completely true, but you can start the process of clustering by doing that. But that would give you, very few samples per class, or basically one sample per class. But what you can definitely do, you can transform, right? You can generate ablations of the same image, right? Instead of doing trivial ablations like random crops, rotations, color jitters, etc. We wanted to do some more, feasible, some sort of, realistic transformations that you would also observe across these re-identification data sets. And that is basically transforming pose by keeping appearance fixed, right? So that we call a spatial pose transformation. So basically you disentangle, this image between appearance and pose, and then you do some sort of a target pose, you input a target pose and do spatial transformation to that target pose. Now, all these images could be, the persons, the same identity in various poses, right? Now, with that, you learn, learn some sort of a, feature representation by training a deep network, and then, is in the second stage, the network learns to map similar features closer in the feature space using using a proposed discriminative clustering algorithm, right? And finally, we show that we can not only beat the state of the art, but we can actually get closer to the supervised reality performance in some cases, which is very interesting. Another video surveillance problem is video anomaly detection. So the video anomaly detection problem is basically where you want to find out activities or something happening in a scene which is not regular, which do not often regularly happen, right? For example, in a parking lot, if let's say or for example in this particular case, maybe you see a car going over this pedestrian walkway, right? So that you would not observe. So it's a one-class classification problem, and we solved that by by basically predicting ahead in time and then comparing what actually happens. So we train our model on normal events and then deploy it on streaming videos and classify anomaly or the abnormal events. So this is done in collaboration with VCL. Another area which could be, of interest is the same anomaly detection but on images. Now this has application on, let's say, industrial, quality controls, for example. So you have this, you know what a bottle looks like, mouth of a bottle looks like, right? So when some process manufacturing defect occurs, for example, by simple computer vision techniques, you'll be able to detect, okay, there is some defect here without even knowing what the defect is. So you don't have any supervision on abnormal sample. All you know is basically what the normal bottles look like, bottle faces. Now, how do? You basically would do the same prediction-based approach, but instead of doing it temporally, you do it spatially. So basically, you mask, take an image, you mask it, take some patches out of it, and then learn to predict the same image, right, on a normal correct image. Now, if an abnormal image comes, your prediction will be not matching the actual correct the abnormal sample here at the output of the decoder, and that would give you an indication of where the anomaly is as well. So I would not talk about this because this is again some work which we have done in collaboration with Professor Venkatesh Babu's group, which is in the area of unsupervised or weakly supervised 3D human pose estimation, from single images, basically, right? So you already know some of them from the previous talk. So this is one area which we are really excited about. So this is what we call data efficient deep learning. Now, what really is data efficient? What is data efficient? So it's a very broad term, right? So now all you know that deep learning or training a deep model, the deeper the model, the more supervision, good quality supervision you would require, right? Now the problem is that often data is proprietary, right? So for example, think about a situation of Facebook, right? So Facebook has trained this fantastic face recognition model on millions of faces, right? Human faces. Now these images are proprietary to Facebook, and if you want, you want to train you have fantastic GPUs, etc., etc. Now you want to train a model as good as the Facebook's model. But you need such a good data set, right? A very large scale and well annotated data set. Now, because these data sets are proprietary, you cannot expect, availability of such a data set at your disposal. You may end up having some publicly available small scale data sets, but not, the biggest and the best data sets, right? However, what you will have access to is the model that is trained on such a data set. So most often or not, these companies, they would release the model, right? These massively large deep models, which is trained on and is capable of leveraging the massively large data set that they are trained on, right? So what happens when you do not have access to the training data, but you have access to the pre-trained models, which is trained on that data? And can you do some downstream tasks, computer vision ML tasks, that you would otherwise require access to that training data, but can you do the same tasks without needing to access the training data, but just assuming access to the trained model, right? So so this is one area which we explored a lot. And this is the first work, again in collaboration with Val Lab, which is zero-shot knowledge distillation in deep network. So knowledge distillation is a problem which tries to mimic the performance of a very deep network, and try to learn the generalizability or the performance that is achieved by the deep network using a shallower network, because a shallower network, if you feed the same large data set, would not be able to generalize that well. It would not be able to leverage the larger data corpus, right? However, you can show that by using this technique of matching labels at the output
space. The data that we're using is ocean data, right? So ocean satellite data. And to start off with, the skills that are needed is probability, linear algebra, tensor flow programming, right? So basically that you can pick up even after you get admitted, but for the interviews we will be looking mostly at probability, linear algebra, and the programming logic, right? So how do you think?
Can you mute? All right, maybe we can start from where we have left from. So, so basically, what we have done is that we have performed knowledge distillation without needing access to the original training data. So we synthesized the training data or some representation of the training data from the pre-trained model. Which we call data impressions, which may not look exactly. For example, this is basically a car, right? Which may not be that well visible from this image, but when you use this synthetic sample generated from this model to train the student network or any network for that matter, you get a close or similar performance to that you could obtain using the original training data. So now you can actually set a target vector that I want some sort of a softmax that is representative of car. Let's say the car probability is 0.9 and the rest is 0, and you have the the trained model that is trained on the original data. You backprop through it and you perturb the input, randomly initialized input image to generate this synthetic samples. Now you use these synthetic samples to perform your knowledge distillation, and you can show that you can obtain very similar performance to a knowledge distillation when you use the original training data samples. Now you can not only knowledge distillation, but you can potentially use the same data impressions to solve many other challenging ML problems where you would require the training data or the original source data set. One is the source-free unsupervised domain adaptation problem. So unsupervised domain adaptation problem does not assume availability of target labels. So what is domain? So domain adaptation is basically when you have a model, let's say a model trained to classify objects, right? Object categories, cat, dogs, buses. Now you have a data set collected from, let's say, Indian roads and Indian scenario. Now let's say you have what a car looks like, what a bus looks like in Indian scenario. Now you want to deploy it, let's say, a completely different scenario, let's say in a Western scenario and so on. And the task is same, the classes are same, but basically there is a lot of visual and semantic differences between these two observations. Now unsupervised domain adaptation tries to adapt this source data set trained model to a very different looking target data distribution, but without assuming availability to target labels. And we solve this problem one step further, where we also assume that I do not even access to the source images, right, labeled or unlabeled, right, because of that same proprietary or security reasons that motivated the work in the first place. And we also have looked into the same another problem of continual learning using data impressions and so on. We have also, Professor Babu has spoken to you about this adversarial attacks and adversarial perturbations, right? And this universal adversarial perturbations, which some sort of data agnostic image agnostic perturbations that you can generate. And we have shown that we can also generate such UAPs or adversarial attacks without having any information of the original source images, but just assuming access to the source trained model. This is another work in collaboration with ValLab, where we looked into a different approach of generating such synthetic samples using a GAN framework. So this is one area which we also explored, which is data-free adversarial defense at test time, where we do not do adversarial training. So what happens is that when you want to make a model robust to this adversarial attacks, right, what you do is that you generate these adversarial samples using your original images, and you train your model and you include this part of samples in your training set. But what happens when you do not want to do that, let's say? So this is exactly where you can do this space-time adversarial defense, where you can detect the samples, incoming samples, as a potentially adversarially perturbed image or not, or a clean image, and then use some sort of a correction of the adversarially perturbed image using a Fourier transform, basically. And that shows very promising performance even without having to train your model with the adversarially perturbed images. And this is another similar work where we not only want to where in this case basically we we look at this again there's adversarial training, but a lot of work recently have shown that there is an inherent bias associated with adversarial attack, which we call robustness bias, and where basically certain subgroups in the data set, maybe based on class or based on gender, are less robust than others. And one very popular way of characterizing this subgroup's robustness by only by checking individual samples' proximity to the decision boundary. So the closer a sample lies to the decision boundary of a classifier or a deep network, the more vulnerable it is basically to be attacked by adversarial perturbations. However, in this work we argued that this measure is not enough basically. Right, and we proposed a holistic approach for quantifying, adversarial vulnerability by, combining a notion of, high frequency components of input images and how that affects the adversarial vulnerability. Right, and we combine, that with the distance to decision boundary aspect, and finally, we show that, you can use this kind of a holistic measure not only to minimize the not only to kind of understand which models are, which samples are more vulnerable, but you can also build a trustworthy system basically, right? So where the human operator can be alerted about any incoming sample that are highly likely to be misclassified at test time, right? So this is one up and coming area which is of very, which are gaining a lot of importance in the modern ML, especially in computer vision literature and computer vision research. And this is some early work into that. So I will not take much time. So I will very briefly talk about, maybe in 5 minutes, talk about some of the problems that we do in, that we look at in cross-modal and, cross-modal learning. So this is, as you all know, the person de-identification we have already spoken about. So where the query and gallery both were containing images, right? Be it thermal or visible, whatever. However, what happens when you do not have an image to query with, right? You don't have an image of a target, right? So in such situations, think about a situation where a crime has happened and some, first person witness. So the witness is giving you a description of, the perpetrator, right? For example, they say that the man is wearing a blue and white striped tank top and green pants. He has pink headphones around his neck and so on, right? So and with this, you need to search your gallery, basically all these cameras, and come up with, the correct matches. So this is an area of text-based person search, which is very, not only, realistic problem, but very challenging as well. And we proposed a solution based on, a joint learning on attribute space as well as latent space, which is identity preserving space, and obtained very interesting and promising results. Another cross-modal learning problem that we look at is basically, a cross-modal query-guided object localization. So what could be a query? So this query could be a sketch, right? For example, this is a natural image which contains person, a dog, trees in the background, and so on. All these are, different object categories which are defined in this, data set. Now, I want to, just localize this dog. I don't want to, in a traditional detection problem, you localize all these, person, tree, dog, etc. Right? Now, I just want all instances of the dog. Now, I don't know what this object label is. I don't know what the dog is. But somebody has given me a sketch, just roughly described, what a dog looks like, a very crude sketch like this. So this is very important problem, especially in situations where these object categories are not really, standard natural objects, like, in industrial applications, again, you want to detect some machine parts and so on, where, you can draw some crude hand-drawn sketches, but it does not match or relate to any natural object category. Also an open world problem where, basically you don't have any training image for the dog, but, you can still query with some sketches. And we proposed a solution based on cross-modal attention between these two different categories, two different modalities, and we showed that we can get promising result by querying with even very crude sketches. And then we further, combine this with, natural language descriptions, the sketches, right? So parallel to this, in addition to this, let's say, hand-drawn sketch, I also, let's say, the query also has a short description, which in natural language we often call gloss. So it's a lightweight handheld collapsible canopy. That's a description of an umbrella, right? So, so all these things, if you combine together and you can somehow capture the complementarity in the semantic space, visual semantic space, then you can potentially do much better. And that is exactly what we see, that when you only query with the sketch, you often end up with a missed localization. However, when you, for example, this carrot, when you query with the carrot sketch, you actually localize the cake, but the out of focus carrots are there, but they are not very nicely they are not localized in this case. However, when you combine with the description, the gloss description of it, you get a better localization performance. We also looked into the classic problem of text question based knowledge KVQA, the knowledge enabled VQA, visual question answering problem, where given an image like this, we want to ask questions like, can I get a sandwich here? Just this image is given. And we have access during training time, a knowledge graph, as well as, these different, object category, basically, a text recognition model, like OCR, right? So we combine an OCR as well as a knowledge graph and do, combine the natural language question with, OCR outputs like word proposals and also visual content proposals, and combine that with knowledge base, which is, a relationship between these different, these different entities, like, the named entities, as well as, these different, categories like restaurant, sandwich, which country it's a brand of, and so on, and finally do a reasoning, using a gated graph neural network, and we get the final answer. So if you ask which restaurant is this, you can get an answer Subway. If you ask, can I get a sandwich here, we'll get an answer yes, and so on. Yeah, so we also look into the problem of domain adaptation, as I mentioned before. And these are some other applications which we have looked into, like, satellite image super resolutions, doing computer vision on a different sensor, which we call an event sensor, in collaboration with Professor Chetan Singh Thakur's group in DESI, where we do activity recognition on event cameras, or neuromorphic cameras, and also do anomaly detection. All right, so you can get more details on each of this work and many other works from our website, which is this. And if you have any question, this would be the right time to ask. Thank you. Any question? All right. If there is no question, many thanks for attending this long session. I hope all of us have been able to give you glimpses on some of the research that is ongoing in various labs across CDS and the topics that we all are very excited about. So, and I really want to wish you all the best for your applications, your graduate school applications and interviews. So thank you. Hope this have been helpful. This session.